So finally, there's a couple more things that we want to do. So if I were to just run this just now, um, what you'd end up doing is, again, you'd start with the height of the tooth tip at 10%, the width of the tooth at 10%, and the angle at 3.19, just about, and then it would go into the FEMM, load in this model, and execute this script down here. Now, this script, as written, basically determines the torque acting on the rotor. This is the default script. So, as you can see, what it does is it uses these commands in here that are actually part of what's called the Lua scripting. So, let's see. Let's go over to this help topics, and in FEMM you have this whole section here called Lua scripting, and these are the commands that you're actually going to be using to do these output scripts. So let's see here. In the magnetic output, so we have 3.4, section 3.4, magnetics post-processing command set. This is what these are the commands that you really are going to be using in this output script. Oops, where'd that go? So for instance, the first command tells you to group select block 2. So if you go MO so here's the actual command that we're looking at. MO group select block and in. So in this case, the rotor is actually the second block. Right? I think the stator is block 1, and the rotor is block 2, and the error is block 3. I believe. I'm not entirely sure. In fact, I think it's written in the Quick Machine manual. So that will actually tell you for sure what the actual blocks are. But anyway, so what this does is that effectively, if I zoom out here, what the MO group block 2 does, it effectively selects the rotor. Okay, so let's look at the next command. The next command says torque equals MO block integral 22. Okay, so if we go back up here, I think we passed the block integral. Right, so here's the MO block integral command, and it's actually the 22th command. So you're doing a steady state weighted stress tensor torque. So essentially what I'm doing in this script is I'm creating a variable named torque, and I'm setting its value to this integral. So I am setting this torque value to the block integral over the torque via weighted stress tensor. Right, so my torque variable is going to be a negative 43.0 whatever Newton meters. Right, so that's my torque. Now this command is actually not within the Lua scripting. This is specific to Quick Machine. And what this is saying is that I'm going to now write out this variable torque to this default file. So the default file will actually be something that we're going to set later on. When you hit this run button, you'll see that you get these sort of files that you want to look at. So right here is the name of the file that you're writing to. Okay, so, but again, our goal isn't to determine what the torque is acting on the rotor. Our goal is to find the amount of flux passing through this point right here. So that's going to be a little bit difficult. Mainly So I guess, sorry, there is a couple of ways that we can do that. Under your MO scripting, or under your Lua scripting, you have this command here, MO get point values X and Y. And what that's going to do is it's going to give you basically this whole table of data based upon that point. So you have A, this vector potential A, or flux, you have flux density in the X direction, flux density in the Y direction, and you have all these other parameters. So for instance, if you look, this is how you would actually use that Lua scripting part. You would say you'd have these variables A, B1, B2, sig. You can name these variables whatever you want, but essentially you need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14 of them. Right? This function right here is going to return 14 values, and the point that you actually want to get those values from are right in here. So let's just say I copy that. I can come back to my scripting thing. I can say this. I'm going to paste that in there. Now, I don't actually want to use this point, right? Because that point is like right here. It doesn't make any sense to use that point. So what I'd actually like to be able to do is I want to say I want to use this point right about there. So now if you look at the top right of the screen, you're going to see something that says position 6.62 negative 2.4. So one thing I can do is I can just type in 6.2, what was it, 6 negative 2.4. Right, I can just type that value in there, and that will give me this point right in here. I guess it's 6.6. Okay, so that'll give me the point right in here, and it'll give me these point values for that. Now, one thing to note is that if, say, we'd also been doing a parameter sweep on the width of the tooth tip, right? So if we were actually changing this tooth tip, then one problem with just typing these numbers in here is that at every time this thing increments, it actually changes this point. So it might move it over here, it might move it over here. So this point is dynamic based upon these parameters that we're sweeping across. So that can be problematic, right? There's no way that you'd be able to put in a fixed point here and guarantee that you're actually even on the stator. So one way around that is to do this, is to right-click on a point that you want, right-click close to a point, a corner point, right? This is only going to work for corner points. So if I say select point, I get this point right here. I get this in this table right here. So now, again, this only works for corner points. So if I were to say right here and I say select point, what I'm likely to get is actually this point right here, right? And that's actually the exact number that I put in there. So, for instance, if I'm way over here, I'm not sure exactly what point it's going to pick out. But, so right here, I'm at position 0.22 and 3.67. But note the value that it actually puts in there. It puts in a 1.17 and a 5.35. So a 1.17 and a 5.35 is right about there. So it did pick out this point. Now watch this point as I move the rotor around. You note that actually changes. The value of this changes as I move this rotor around. And this is very important because if once I create this point here, I can basically track it as this tooth moves around. It's not necessarily in this circumstance, but it doesn't matter. So in order to use these points, now all you have to do is just type in a name. So I'm going to say, I'm going to give this name point 1. Oh, that's 2. I'm going to call this one point 2, call this one point 3, whatever. Doesn't really matter, but you just have to give it some sort of unique name in here. And then to actually use it, I would just say point 1. Now, what this will actually do is before it tries to execute this script, it will go in here, try to find any instances of point 1 and do a textual substitution with 6.6 comma negative 2.34. Right? So every time that this tries to execute, it will do a textual substitution for this point for basically whatever this value is right here. So, okay, so now we have all of these, all the properties at this point set up in our variables. Now we need to output the flux density to a file. So let's go here. So I can say I want to write to the default file, and I'm going to, now, since I've already written torque to this default file, the next thing I want to write is a comma. So I'm going to say quotation, comma, space, quotation. Right, so that'll write out a comma, and then I'm going to write out the actual flux density. Kind of. It'll actually be the flux density squared. So I'm going to say I'm going to take B1, I'm going to square it, then I'm going to add it to B2 squared. And remember, B1 is the flux in the x direction, B2 is the flux in the y direction. So if I want the total flux density, I have to square these two and add them together. And technically I'd have to take the square root. But I'm not sure if there's actually a square root command in Lua or not. But it doesn't really matter for this sake. I'll just output the squared version of these two. But note that you can do simple arithmetic with these Lua scripting, and it's going to know what to do. So here I'm squaring this value, I'm squaring this value, and I'm adding them together. Likewise, another thing I could have done is I could have said this. I could have said B equals B1 squared plus B2 squared. Right? And now B is holding my flux density, so I could just say this.